Hello everyone. I will give a presentation entitled Simultaneous Acquisition of High-Quality RGB Image and Polarization Information using a Sparse Polarization Sensor. First, let me explain the challenges. The figure on the left shows the structure of a conventional polarization sensor. This is an RGB image and is of low quality. This is because pixel binning reduces resolution. Sensitivity is also reduced by polarizers compared to normal sensors. The naive solution to this is to make the polarization pixels sparse. But, there is a trade-off between the quality of the RGB image and polarization information, as fewer polarization pixels reduce the degradation of the RGB image but decrease the resolution of polarization information. In the figure on the left, the polarization pixels become more sparse as you move down. You can see that the polarization information is becoming lower and lower quality. Therefore, we propose an approach that resolves the trade-off by sparsely arranging polarization pixels on the sensor and compensating for low-resolution polarization information with higher resolution using the RGB image as a guide. As a result, we can get both higher quality RGB images and polarization information. This is an overview of the proposed methodology. Our proposed Stokes network architecture, SNA, consists of an RGB image refinement network, RGBRN, and a polarization information compensation network, PCN. Sparse polarization sensor has polarization pixels scattered on a normal RGB sensor. Therefore, when demosaicing is performed, artifacts are generated in the polarization pixel areas. Such demosaic artifacts in RGB images interfere with the densification of polarization information. Therefore, a refinement network is used to clean up the RGB image. PCN compensates only for polarization information S1 and S2. We use the feature transfer block, FTB, to convert the features generated in the first branch into a form suitable for the second branch. Furthermore, considering the global and visual features of the scene, an attention type feature aggregation block, AFA, is applied to give higher weights to important channels at the encoder side and add them to the features at the decoder side, allowing for more flexible learning of the representation in the first branch. This is about the dataset used for training. We took both real-world and synthetic datasets to train the network. This is a larger scale than the conventional polarization dataset. Synthetic datasets can be created automatically by generating objects using Houdini to obtain large amounts of data at no cost. We confirm the superiority of our network by comparing it to state-of-the-art methods for similar tasks such as depth completion and upsampling. Comparisons are also made with generic methods such as UNet. Our results outperform conventional depth completion networks in performance, especially near the edges. Finally, we confirmed that our approach could simultaneously acquire higher quality RGB images and polarization information than conventional polarization sensors, resolving the trade-off between the quality of RGB images and polarization information. Let me close with a summary. We proposed a new sparse polarization sensor structure and network architecture that compensates for low-resolution polarization information to acquire high-quality RGB images and polarization information simultaneously. The results of this study are based on simulations. In the future, we intend to consider prototyping our sparse polarization sensor to validate its practical application. Based on this research, we believe that polarization pixels could be incorporated into many cameras in the future. Thank you for listening.